So a bit more on the transformations. Dilations. So when we're stretching curves, if you like. So if it's a horizontal stretch, then it's the domain we're playing with, so the x is what's going to change. We say it's x divided by a. So a is the factor of the dilation. So we replace x with x on a. It's going to be stretched horizontally, so if a is greater than 1, it'll become shallower. If that a was less than 1, imagine pushing it in now, it becomes steeper. So that's the effect of the curve. So the domain may well change, because if it had an asymptote somewhere, because you're stretching it out or pushing it in, that asymptote's also going to move. But the range won't change. It's going to do nothing to the height of it, because all we're doing is pulling it sideways or pushing it in sideways. So the other way around, if I did want to stretch it vertically, now it's the y that I'll replace. Again, I'll divide it by the factor. Y over a is equal to function x. Replace the y with y on a. Or another way of thinking about that is y equals a times function x. But this time, if it's bigger than 1, it becomes steeper. So again, if you think of the shape and you pull it up, that's becoming steeper. But this time the domain won't change, because all we're doing is pulling up, but the range, the y values are changing. Let's have a look at this then. It's the very basic graph of y equals x. There it is. So y equals a half x, or x on 2 if you like. So I'm stretching it out, it becomes a shallower line. Y equals 2x, well now that's the same as saying x divided by a half, so it's a number smaller than 1. Bang, it now becomes a steeper curve. It doesn't have to be just lines, any curve. So I could do the same thing with the parabola. You got y equals x squared, y equals half x squared. I'm pulling it out, it becomes a shallower graph. Whereas y equals 2x squared, becomes a steeper parabola. I have to draw x squared plus y squared on 4 is equal to 1. Basic curve is the circle x squared plus y squared is equal to 1. What have I done to it? I've changed y squared into y squared on 4. Or another way of thinking about that is y on 2 all squared. It's the y that's been changed, so I've stretched it vertically, and it'll be by a factor of 2. So we're going to stretch it out, and we end up with an ellipse. They asked this one a few years ago now. So here was the original curve. They said, alright, we now want you to draw y equals 4 times function 2x, making sure you indicate where the x-intercepts and the coordinates that they've put there, that turning point, gets moved to. There's the original graph, but we want 4 times function 2x. What have we done to it? I could rewrite this so I can see the transformations better. So y over 4, we have a dilation in the vertical direction, but then it's going to be function x divided by a half. So horizontally, the factor is a half, so I'm pushing it in. It'll become a steeper, there it is. All of the x values are going to be halved. The y values staying the same. So that x-intercept of 6 became 3. That turning point, which had an x-coordinate of 4, is now 2. Okay. But we also have a vertical one by 4. So now we're going to stretch it out by 4. The x values now will stay the same, but the y values will be a factor of 4. So that negative 8 would end up going down to negative 32. And there's our new graph. So enlargements then. We've got a shape, we're just going to enlarge the shape. And that's when we apply the same factor in both directions. So we dilate both horizontally and vertically by the same amount. So you can think of it saying, well, I'm going to replace both the x and the y with x over a and y over a. So we've got a circle, x minus 1 squared plus y plus 2 squared, and we're going to enlarge it by a factor of 2. Now all these enlargements are done using the origin as the centre of the enlargement. Find the new equation. So here's the original equation. I'm going to enlarge it by a factor of 2. So the x I'm going to divide by 2, and the y I'm going to divide by 2 as well. Let's make that look a bit neater, and I'll end up with x minus 2 squared plus y plus 4 squared is equal to 4. There's our new circle. What we've got to be careful with, not all of the transformations commute. What do we mean by commute in mathematics? Any operation commutes if the order that you do it doesn't matter. For example, addition and multiplication commute. 3 plus 4 will give you the same answer as 4 plus 3. 3 times 4, 4 times 3. However, subtraction and division don't commute. 3 minus 4 is not the same as 4 minus 3, and 3 divided by 4 is not the same as 4 divided by 3. So not all operations commute. In transformations, you can do it in any order, but the exception is this. If you're going to do a dilation and a translation in the same direction, then it doesn't commute. You've got to do it in the correct order. I'll show you. Here's our function. Now, if I was to move it to this curve here, 1. So what have I done? I've said I'm going to reflect in x equals 0 and then shift it right. But what if I did it in the other order? If I shifted it right, then reflected it. Because reflecting is actually a dilation of a factor of -1. So reflection is actually a dilation. It would end up over here. So that's where if I shifted it right first and then reflected through the y-axis, we get different curves. So that's the one we've got to be careful with. Let's work out the equation when we get our parabola, y equals x squared, and then what we're going to do is we're going to shift it up 1 unit, then reflect it vertically. So x squared, if I shift it up 1, we know will become x squared plus 1. Then I'm going to reflect it vertically. So the whole thing's being reflected vertically, I'll end up with minus x squared plus 1. And so there's our new equation. Whereas if I did it the other way around, if I reflected it vertically first of all, then shifted it up 1 unit, the x squared would go to minus x squared, and then I would shift that up 1, we get a different parabola. There is y equals 1 minus x squared, 3h and 3i. That will do us for today.